Hello friends, welcome to our channel. So in this video, we're going to look at problem 1462, cost schedule 4. This is a graph problem. So in this video, we're going to use breadth-first traversal to solve this problem. And in between, we're going to use dictionary to help us get the result. So let's quickly go over the problem statement. So basically, we have a number of courses, and in order to take some courses, you have some prerequisites. So these prerequisites are represented by a list, right, given here. So basically, if you have something like AI, BI, which means AI is a prerequisite of BI, and the relation is transitive. For example, if A is a prerequisite of B and B is a prerequisite of C, then course A is also a prerequisite of course C. So basically, we are given a query array. So it's represented by this UJ, VJ. So we want to answer if UJ is a prerequisite of VJ. So we want to return a Boolean array answer, right? So answer J is the answer to this query. So here you can see the first example. So 1 is the prerequisite of 0, right? So, but 0 is not a prerequisite of 1. So that's the first example. So in the second, let's look at the second example. In the second example, so here we have two courses. So there's nothing, this empty prerequisite. So this return is all false, right? So in example 3, so we have 3 courses, and we see that this relation. So we can see 1 is a prerequisite of 0, and 1 is also a prerequisite of 2. So this two truths. So let me also explain the constraints. So here, the number of courses is bounded above by 100. So basically, if you have 100 nodes, so this is not a very large graph, because if you have a complete graph, that's the upper bound of the number of edges. So, and here, all the pairs are unique, and the query length is bounded by 10 to the power 4, right? And the UI does not equal to VI. That's some consistency assumption. So with that said, I guess we are ready to look at the coding. So the coding actually is very routine. So basically, we build a graph, and then we do breadth-first traversal, and then we use some dictionary to get all the results for each node I, and each node J. Then we just return the corresponding answers to the query. Let me break into sections. So graph, build graph. So this is actually very straightforward. So here, let me see. I changed this to be n, the number of courses, and I changed the prerequisite to be p, just for convenience of typing. So here I'm going to use I set for I in range n. So here the key is the nodes or the classes, and the set represents the neighbors or represent those nodes with I as a prerequisite. And then actually we can iterate over the prerequisite for ij in p, right? So basically graph I should add j. In other words, I is a prerequisite of j. So now let me get a dictionary. Let's call it reachable. So this dictionary, I'm going to use collections default dict. So here I'm going to use a set. So you can regard this as a function, or you can use it as a container. This is the one way of writing. You can also write it like this: lambda map everything to be an empty set, right? But here, write set. That's actually more convenient. So now I'm going to write a helper function, write a BFS function. So this is actually very standard. So here, let me do BFS. So start from a node I. So I'm going to use iterative format. So let's visit it. It's a set. And then I'm going to use a queue collections. I'm going to use a deck. So here, this is the source I. Then basically the very standard iteration. Val node, val queue, we get the node, this queue pop left. So then we do some check, if node not in visited. So we are going to add this node to visited, right? And then we are going to check the neighbors. So for neighbor in graph node, then if neighbor not in visited, so what we are going to do, we are going to append this neighbor. Then what we return actually is the set, so visited. So basically, you do traversal, you can get all the follow-up causes starting from I. In other words, I is a prerequisite of the causes in this visited site. So with that done, what we do? So basically, we do traversals, do BFS for every node, for each node I, or for each class. So this is actually very simple. So for I in range M, right? So then I do traversal. So basically, I'm going to do reachable I. I'm going to set it to be BFS I, right? So actually, you can use union with reachable I, union with this BFS I. But right here, this would be sufficient. So we can do reachable I, union with BFSI. This is also okay. I guess this one is more. Both are very very logically sound, but depends on. Let me use the first one. Once you do this, then you can prepare the return. So let me use a result. So basically, for ij, right, in the queries, then what you do is you check if g is in the neighbor of I. If so, I is a prerequisite of g. So basically, I'm going to append if g in reachable I, right? Notice that this is given a Boolean value, right? So then we just need to return the state of this result. So that's the full code for this problem. Actually, it's very straightforward. You build this graph, you write BFS traversal function, and then you do BFS for each node, and then you prepare the return. Before we make further comments, let's first run it. Queries, let's see, line 38. Queries. Yeah. Let's see. This will be right? Yeah, it passes all the three test cases. Now let's look at the generic case. Yeah, it passes all the cases. So now let me test this one. Yeah. So actually, I guess these two are exactly the same actually, but it's a tiny bit of thought process difference. But this is a minute point you don't need to pay attention to here. So with that said, I guess that's about it. So if we give a quick summary, so here we used the standard breadth-first traversal to address this problem. But here I want to point out to you this part. So notice that using a dictionary to get those informations and then retrieve those informations actually is one ingredient. So I feel that introducing this dictionary brings us a lot of convenience. So with that said, I guess that's it for the current video. Thank you for watching.